Okay, we're in 1.8 and we're doing something called the intermediate value theorem. Now, I need to be clear that the intermediate value theorem is important in and of itself, but it's not going to be really important to us in calculus until we learn something called the mean value theorem. And then what we'll do is we'll put those two theorems together to make some pretty cool observations about how things move. Okay, so in calculus, we're going to need something called the intermediate value theorem, and we're going to ask some questions on it right now, but we're going to come back to this later in the semester when we learn something called the mean value theorem. So it's one of these theorems that's going to come up again. Now, this theorem, well, let's just do it. Let's just do it. Okay. The intermediate value theorem, you can abbreviate it IVT. Suppose you have a function that is continuous on a closed interval. And here's the thing, guys. When you're doing calculus, it's got to have a continuous function, and it's nicer if it's closed, okay? What does that mean? I don't lift my pencil up, and the endpoints are filled in, okay? If they're open, then this theorem doesn't work, and if there's breaks in the function, like we just talked about with discontinuity, this theorem doesn't work. So what we really want to do is say, okay, suppose there's no points of discontinuity, and at the endpoints, they are closed. So it's just, literally, it's like I put my pencil down, I draw the picture, and I put my pencil down again. No opens, no breaks, nothing weird like that. Then this theorem works. Okay? Suppose that it's continuous on a closed interval, A to B, and then n is any number between f of A and f of B. But we have to make sure f of A doesn't equal f of B, okay? F of A can't equal f of B. Then there must exist a C on the interval A to B where f of C equals n. Clearly true, right? Okay, this is a lot of stuff, and if it makes sense to you, you're pretty smart. First time I read it, I was like, when I was your age, reading this, what does it mean? It really is super common sense. It's just when you get caught in the verbiage, you can kind of lose the meaning of it, okay? It's not that big of a deal. Here's what it's saying. If you have a function, let's do an example here. Now, I'm going to do one where f of A is bigger than f of B, and then one where f of B is bigger than f of A, to illustrate this idea of what a betweenness, right? So the theorem says it's got to be a closed interval, and we just discussed that. This is a nice closed interval, so is this one. Now, what the theorem says is, as long as I choose any n between these two, as long as I choose any n between those two, no matter what I do, there's going to be at least one C value that is between A and B. Okay? So, if I choose any n, I can choose any n, right? I could choose n up here, I could n down here. Now, that is what the theorem says. You have to. Now, that doesn't mean that obviously if I chose n up here, it would still work. Okay? I could choose n's down here. But that's what the theorem is very specific. It's saying as long as you stay between f of A and f of B, no matter what n I choose, it's going to map onto a number between A and C. Okay, that is just what it's going to do. Okay. Now, let's do one where f of B is bigger than f of A. Now, and what I want to point out this, there exists a C may be more than one C. Okay, one of the things is you're guaranteed, if I choose any number between here and here, between. Now notice, now you might be wondering, why worry about between so much? Notice I didn't say f of A, f of C, f of B, because I don't want to always assume that f of A is less than f of B. I am okay on the x value, but notice that I want to have the idea of what we call betweenness. It doesn't matter whether f of A is bigger than f of B or f of A is bigger than f of B. Now, if I choose any number here, it's going to map down onto a number here. Now, you probably noticed, it can happen multiple times. Yeah, the theorem says at least once. Okay? But it doesn't matter where, in other words, I could choose another n here. I am guaranteed that every time I pick a number between those two, it maps down between A and B. That is all the theorem is saying, okay? And you can see that that's going to be true just visually, I think. Now, one of the things is like I said, it may work outside of that interval, but there's going to be some point where it doesn't, right? And so what we're doing is we're kind of doing this in broad strokes. We're saying this is the only area that you are guaranteed. Now you might get one down here, you might get some up here, but that is what you're guaranteed. Now, the biggest mistake that students make on this theorem is they do it backwards. Don't do it backwards, because backwards doesn't work, right? Just because you're between A and C doesn't mean you're between f of A and f of B, right? So, be aware that the theorem does not work in reverse. Don't do it in reverse, right? Don't do it in reverse, right? It doesn't work in reverse, okay? Now, you might be going, Mr. Peters, this is kind of weird. Like, it's actually important. I'm gonna simplify it down to the type of things you're gonna have in your homework. What we want to do now is see what this does. And now, you've done this before in your life, probably before. When you do this in computer programming, they call it the bisection method. Okay, when you're trying to solve equations if you're trying to do mathematics on a computer and trying to find zeros. So let me show you what I mean. I'm going to kind of illustrate this by what you're going to do in your homework, and then I'm going to kind of extrapolate this onto another idea, okay? Where this idea eventually goes, if that makes any sense. So let me move this camera over here. Let me see if I can get set up here. This is basically how it works. And then when I do this example, I think you'll start to go, oh, yeah. You guys, going back to the theorem, the theorem says n. You guys, it works for any of the n's, but really this is almost always used when we're talking about n being 0, and you'll see that in the example that I'm about to do. Okay, you'll kind of get why in math we have this theorem, but this theorem really is a theorem that's used when we're doing trying to figure out when a function is equal to 0. Okay, so here is how this is going to work pretty much in your homework. Now I need to be clear that they'll sometimes ask it in funky ways on the AP exam, so I might do a second video on like, hey, this is how you normal people do this, and then I will do maybe when I finish up this idea, this is the basic idea on the intermediate value theorem, I might follow it up with a short video on here are some of the weird ways they ask this on the AP exam. Okay, now I might not do that video because they actually usually ask these questions on something called the mean value theorem, which we haven't learned yet. So I kind of want to go through and look at some old AP questions before I make that other video. So if you have a video for Friday, it's because I found some. If you don't have a video on Friday, that means I think we're pretty much covered until we cover this again. So you might not have a homework video on Friday, but you might. I haven't decided yet. Okay, I got to kind of look at things. Okay, so here's what we got. Here's the common sense. Let's do the intermediate value theory through common sense. Okay, does this parabola x squared plus 2x minus 5 equals 0 on the interval from 1 to 2? Okay, so now you want to kind of think of this here as the function. Going back to, we had this function on a closed interval. And then you want to think of the 1 and 2 as the A and the B. So you kind of want to think of this 1 as A and the B as 2. So this is the closed interval from A to B, and there's the f of x. So going back to the theorem again, theorem says, suppose x squared plus 2x minus 5 is a continuous function on a closed interval. And it is, right? Now you might go, how do I know it's continuous? Remember, there's only 3 things that mess up our world when we have an equation, right? You don't want to divide by 0, you don't want to take any square roots, and you don't want to take the logarithm of a non-positive, right? You know, you can't take the square root of a negative, you can't take the logarithm of a non-positive, and you can't divide by 0. Those are the only 3 things that really mess up our world, right? That's why all those questions we've had with this continuity had all that division in it, right? So just be aware of that. Now, you might go, Whiskers, what's the difference between a non-positive and a negative? The difference between a non-positive and a negative is 0, right? 0 would be in the group of non-positives, but it would not be in the group of negatives. But don't worry about that too much. Notice that we have a regular old polynomial here, right? No matter what number I put in, I'm going to get a number out, right? So it's nice and continuous. There's a number, they're all connected and everything. We're never dividing by 0, so there's no breaks in the function or anything like that. So what the theorem says is, as long as, and this is n is going to be the 0, okay? So what I'm going to do here, what the theorem says is, as long as 0 is between f of 1 and f of 2. Now, I'm going to kind of overgeneralize here, because I already did the question earlier. I know f of 1 is going to be less than 0, and I know f of 2 is going to be bigger than 0. So, and if it wasn't, you just have to reverse it, right? So notice when I put 1 in to this function, 1 squared is 1 plus 2 minus 5. I'm just checking to see that this is true, okay? And I put 2 and I get 4 plus 4 minus 5. So I get negative 2, yes. So now this is probably, you guys, this probably isn't the best way to write this, I apologize. You probably should just do this. F of 1 is negative 2, and f of 2 is positive 3. Okay. So I know that 0 is, and I know 0 is between negative 2 and 3, right? 0 is between negative 2 and 3. So what that means, let's go back here. What that means is there's got to be some c between 1 and 2 where f of x equals 0. So that means, just changing the thing, that then I can conclude, since this is negative and this is positive, and remember, I didn't do that. Let me move the camera back when I talk like that. So when f of 1 is negative and f of 2 is positive, and 0 is between f of negative 2 and 3, then we know that sometime between 1 and 2, there's got to be some, in other words, if f of 1 is negative 2 and f of 2 is 3, you can't go from, look at the graph on this. Look at the graph, guys. If f of 1 is negative 2 and f of 2 is 3, if I have a continuous function, I can't get from here to there without passing through 0, can I? It's just not going to happen, right? So there's got to be some c value. There's got to be some c value where this is going to be 0. And again, you probably have done stuff like this before in your life, where you want to know whether there was a root on an interval, and maybe you have never done that before. And the way you figure that out, of course, is you say to yourself, well, if one's positive and one's negative, I can't get from one to the other without passing through 0, so I know there's got to be a 0. Now, we don't know what it is. We just know that it exists on that interval. Okay?